Newton's law of universal gravitation is an important part of our discussion and understanding circular motion, and just in general how gravity works. So the main question here that we're looking at, if the force of gravity is being exerted on objects on Earth, what is the origin of that force? And so it's important to think through that. Newton wrestled through that, and if we consider, people on the different parts of the world here, they're all being pulled to the center of the Earth, and so Newton realized that the force must come from the Earth itself, and he also realized that it must be what keeps the moon in orbit as well, and so. The origin of that force is the Earth itself, and it turns out the mass of the different objects is the cause. And so, the Earth exerts a downward force on you, and you happen to exert an upward force on the Earth. And so, if we, jumped into the air and the Earth pulled down on me with 700 newtons, I'm pulling on the Earth with 700 newtons. Now, the inertia of the Earth is huge, right? So you're not even going to be able to get close to detecting any kind of movement with the Earth, but with me, right, it would be pulled down, pretty quickly, and so, there's such a disparity in masses, as you're not even be able to tell, but we definitely can tell with the moon, right? So if the moon is on the side of the Earth where we are, the water is being pulled up, and so we have high tide, right? And so, but if the moon is on the other side of the Earth, we have low tide, where the water recedes and it's pulled on the other side of the Earth. The way they figured out the strength of this force is with the Cavendish experiment. This is pretty ingenious how they set this up. Relatively simple. They had a fiber, mirror that's attached to the fiber, light source that would hit the mirror, bounce off, and then go to a scale, rod with two masses. And so we bring one of the masses close to the other one, and it would actually, these two masses would attract, make the rod to actually turn, and as it did, the mirror would turn, and then as the mirror turned, the scale would show a deflection at a different angle, and by knowing the masses of these, by knowing how far apart they were able to figure out the force of gravitation between the two of them. So what they discovered was the gravitational force is proportional to both masses, so directly proportional to both masses, and by observing planetary orbits, Newton also concluded that the gravitational force must decrease with the inverse square of the distance between them. So, we're going to see lots of squared relationships. In this case, it's an inverse squared relationship, where if you end up doubling the radius, how far apart they are, you only get a fourth of the force, or tripling the radius, you get a ninth of the force. It's an inverse squared relationship. And so this is the relationship. We have the force of gravitation is equal to the gravitational constant G, which is 6.67 times 10 to the negative 11th, times mass 1 and mass 2. So we multiply the two masses together and divide by the radius in meters between them, and that radius is squared. All right, so let's try this out with a sample problem. The universal law of gravitation works for any two masses. We can find the gravitational attraction between them. And so let's go ahead and do this with a example where we have your mass and then the mass of a desk. I want to figure out, how much force of attraction is there between you and the desk, and so and at 2 meters away. So we'll see the this would be a good example to see the strength of them. So go ahead and pause the clip, and when you're ready to see the final answer to check your work, you can hit play to continue. Okay, so we've got our gravitational constant, multiply two masses over 2 meters squared, and we should get 2.22 times 10 to the negative 8 newtons. And this is an extremely small number. I'll just write it out here. So we have, let's see, 1, 2, 3, 4, 5, 6, 7. Very, very, very small amount of force. So you're not even going to be able to detect that or get close to detecting that. Okay, so let's go ahead and try this now with something that's more massive. We have a 1,700 kilogram car, and let's say our mass is 70 kilograms, 2 meters away. How much force of gravitational attraction would be there? So go ahead and pause the clip and go ahead and calculate that out. You can hit play when you're ready to check. Okay. We should get 1.984 times 10 to the negative 6 newtons. Again, a very, very, very small amount of force. You're not going to be able to feel that.